Seat of Professor Julio Navarro. He is the colloquium speaker this month, and Professor Navarro is currently a professor at the Department of Astronomy at the University of Victoria in Canada. Professor Navarro was born in Argentina, and actually he has two nationalities. He is Argentinian and he is Canadian. Professor Navarro finished his PhD at the Universidad Nacional de Córdoba in Argentina in 1990. Then he moved to Harvard in the US for a couple of years. After that, he moved to United Kingdom, and he was working for two universities, the University of Cambridge and the University of Durham. And in 1994, he moved back to the United States. Particularly, he moved to the Stewart Observatory at the University of Arizona. After 4 years, in 1998, he was working there at the University of Arizona, and in 1998, he moved to Canada, to the University of Victoria, where he got a position as an assistant professor. After a few years, he got the professor position at the University. Professor Navarro has been working very recently at the University of Massachusetts for 1 year. So this is why you see in our webpage that the affiliation of Professor Navarro is the University of Massachusetts, but this is actually wrong. He is back to the University of Victoria in Canada. Professor Navarro is an expert on cosmology and cold dark matter, which is the topic of his talk today. He has published more than 110 refereed papers. This is a very long trajectory, actually. And his work is very well received by the community. Actually, he has received more than 13,000 citations. So thank you very much for Professor Navarro for visiting us. And
well, thank you very much for coming and for inviting me. You made me feel so old. I didn't realize I've been in so many places over so many years. Anyway, so what I'd like to talk to you today is some ideas about, the relics of what we can make of the cosmological context in which the Milky Way may have formed. And I guess you've heard ideas of, how structure in the universe forms through cold dark matter, hierarchical clustering. I'd like to talk to you a little bit is about some of those the imprints that kind of formation process may have left on the Milky Way. So this is the Milky Way as you see, of course, in the infrared. And this is the Milky Way as you've seen it, as you'd see if you were to have a dark matter sensitive eyes. In other words, this is the disk and the bulge of the Milky Way, and the rest is just the dark matter halo. So the idea is that in order to understand, how this thing was put together, which of course, is what drives many of our interests, we need to understand how all this thing was put together. And this is a kind of picture, which is more of an artist's impression, goes all the way out to what we call the virial radius. And I'll use that concept a few times over the talk. So for those of you who are not initiated in this, the virial radius of an object is more or less the radius at which a particle would take about the age of the universe to go around once on a circular orbit. Okay, and that sort of defines the region where the region of what a system could, be virialized, could be an equilibrium from the region where things are still either expanding or collapsing for the first time onto the object. So this is the way in which we believe these things form. This is a little patch of the universe, which was selected so that it will actually, at the end, had redshift. At the end, it will contain a dark matter halo, more or less of the size of the Milky Way. You'll see how this thing evolves. And the jagged boundary here is just because we chose a particular part of the universe, in a much larger box. And this is how things form. In cold dark matter, the structure that exists on all scales. So the small scales collapse first, then all the scales start aggregating through mergers into bigger and bigger and bigger objects. Okay, so the kind of things that are sort of the natural, progression in the formation of structures in cold dark matter is this idea that structures form from the bottom up. You form small things first, and then those small things are already collapsed, aggregate into larger and larger units. Okay, so in other words, a substantial fraction of the mass of any object you'd have thought is accreted through mergers. And another interesting thing is that a significant amount of substructure, you can see over here, actually remains in this halo at a redshift of 0 at the present time. Okay. So that gives you an idea of how these things were put together. You know, the idea of the hierarchical formation and assembly of an object clearly contains a lot of several episodes, you know, of formations. How do galaxies now form in this picture? All that showed you before was called dark matter. Now, galaxies presumably form through the collapse of gas. You know, gas is about 10-15% of the matter in the universe on large scales. Therefore, it will follow just the dark matter. This is a picture of something like what I showed you before, where but on a much larger scale, this is now a couple of commoving megaparsecs across. You see is that you form, for example, several dark matter halos here on this volume, and the gas on large scales more or less follows the same kind of distribution. Of course, gas is different from dark matter in the sense that it behaves as a collisional fluid. In other words, gas cannot interpenetrate. If you throw two balls of gas onto each other in a merger, for example, the gas will stick in the middle, it will shock, it will transform its orbital kinetic energy into heat, and that heat can either be dissipated, things like that can happen. And what we think happens is that as you form a system, as shells of matter collapse to form a virialized object, a dark matter halo, of course, the baryons, the gas, cannot interpenetrate, shocks, heats, and this heat is emitted through radiation because the gas is sufficiently dense. And because of that, it loses its kinetic energy, it loses thermal energy through radiation. Because of that, it actually has to collapse to the center. As it collapses to the center, now collisions between atoms become more important because collisions are just a rho-square process. The gas becomes denser, emits even more at a higher rate, and loses its energy. And this becomes a runaway process in which all the gas, basically, that can participate of this cooling, runs to the center in a runaway process and forms at the center a galactic disk or a gaseous disk. You can see this happening in these simulations. Simulations actually, the only thing they have is in their as physical process simulated are just a radiative cooling. You can see that the gas actually settles at the center in a very thin, rotationally or centrifugally supported structure, whereas the dark matter actually remains more or less like a spherical puffy ball. Like if you go from center to center, you see that most of the gas actually collapses in the center and form these rotational supported structures. So that's the way in which we think, disk galaxies form within these halos, and the structure. I mean, the story, of course, is not over then. What happens is that these gaseous disks that you see over here, we believe, become unstable through the formation of stars. And when you form stars, basically, all you do is you just take gas, which is basically distributed more or less across the face of the galactic disk, and you make it into tiny little balls, which are now have very, very tiny sizes compared with their mean separation. In other words, when you turn the gas now into stars, into these tiny little balls, the collisional property of the fluid, in other words, this idea that you cannot interpenetrate two clouds of gas, is lost. The size of a star is so tiny compared with the mean inter-star separation that you can throw now two balls of stars into each other and they will behave just like dark matter. Now, why is this important for this process? It's important because if you form now stars on these disks, of course, the stars will just inherit the motion of the gas. The gas is on circular orbits because that is, the state to which you will get if you allow, a fluid to lose energy and conserve angular momentum. In other words, circular orbit is the state of minimum energy for a given angular momentum. And so all stars will go around on circular orbits. Now, what happens during a merger is that you have another source of energy, which is the orbital energy of the things that are colliding. Now, this orbital energy gets transferred to the internal energy of the motions of the stars. In other words, you're given energy to these stars. This energy cannot be dissipated anymore because you've lost this collisional, property of the fluid. Stars cannot collide between themselves and get rid of the energy through radiation. They just have to follow more or less orbits like dark matter. Therefore, if you take stellar disks, disks of stars, and collide them together, the stars cannot remain on circular orbits. They have to move on to different kinds of orbits. That is why we think that disks of stars, when you merge them together, form something like spheroids. So in this, very broad-based picture, the connection between morphology of galaxies and this hierarchical formation goes as follows. At least in a very pedestrian or a bit of zeroth order approximation. Gaseous disks form at the center of dark matter halos, that turn into stars, and therefore then when those disks merge into bigger and bigger systems, you end up forming spheroids. So you start with something like this, you merge two of these together, you form a spheroid, and then if you get more gas accreted into the system, this can be regenerated, and you can have spheroids with disks around it. So that is kind of the simplest thing you can say. Now, so what does that imply for this? It's interesting because if you follow this line of argument that I was trying to give you about stars that go on circular orbits, is good because say, oh, okay, they can go, for example, to something like the galactic disk, the Milky Way, and say, I'll find a star that is on a circular orbit. Now, if I can find the oldest star that is on a circular orbit, then I can say when the episode of the last major merger occurred in this galaxy. Because if a major merger had happened after that, this star would not be in a circular orbit anymore. Okay, so finding stars on circular orbits and being able to date them, not ascribe an age, is like measuring the age of the last major merger of an object. And that is, an interesting idea. So let me just show you now how that this, kind of ideas do work, when you do a simulation that now, incorporates many other physical processes like, the formation of stars, feedback from the evolution of stars, etc. So this is, again, just a simulation. And what you'll see is two different projections of what is originally a small patch of the universe. Okay? And we'll see we'll follow the expansion of the universe here. There will be a little bar here will tell you how big the object is. And what you'll see is that, of course, the universe expands. This tiny little patch we selected to be the site of the formation of our galaxy evolves, expands. We have two orthogonal projections. You can think of this as an X, Y, and X, Z-like projections chosen in a particular way that I'll explain in a minute. You can see how this small-scale structure of the universe gets imprinted very early on, and then how all this gas gets accreted into bigger and bigger objects. Now, as stars in dense regions, we allow the gas to turn into stars, as I explained, and these stars are colored by their age. So they're born as blue little particles, and then as they age, as time progresses, they become yellowish, green, and eventually will be red. And you'll see here that I'm only showing actually the gas on the stars. Of course, there's dark matter as well, but it's not shown just for the purposes of clarity. And you see here is that you saw that some of these stars are actually forming disks. These disks actually started merging, start creating these spheroids, and now more gas keeps flowing into the system. Now we're only focusing on the very inner region, so that this gas, a lot of gas outside. And you can see how the gas starts assembling again onto another disk. And the two orthogonal projections were chosen so that this one will end up showing the disk edge on, and this one will end up showing the disk face on. You can see how the gas basically settles onto a rotationally supported structure, and the young stars are just following the gas. So the blue and green particles, or dots here, are basically tracking each other. Now the red ones are the stars that form early on. Okay? Those are formed before all these major mergers and all this stuff happened. And therefore, you'll see at the end, those were actually ended on a spheroid. Let me go back to. So, as I said, it's interesting. So, a couple of things here. In this Milky Way-like galaxies, then, if the movie that I showed you is any representation of what might have happened in reality, then all these galaxies had an early period of merging activity, and followed basically later on by quiescent accretion that led to the formation of the disk of the galaxy. Okay, we know the merging is still ongoing, so some parts of this has to be true. Sagittarius galaxy, has been accreted presumably fairly recently into the galaxy and is now being disrupted by the tidal field of the galaxy. And let's go back to this idea. Then these galactic disks, we can use these stars in circular orbits to date the time since the last major merger. Okay, so like, we apply that to the Milky Way and say, well, let's go to the Milky Way. We can actually measure distances, motions, etc. for stars that are very nearby the Sun. We know the Sun is more or less going to circular orbit. So the Sun is, whatever, 5 giga-years old or something. We say, okay, well, the Milky Way has not had a major merger in the last 5 giga-years. But they're older stars than the Sun in the solar neighborhood. So I can play the same game and go to a catalog of stars, have their ages, and just plot them and see which ones are on circular orbits. And this is from the Geneva-Copenhagen catalog of about 16,000 stars with good motions, all within a tiny little circle around the Sun, about 100 parsecs or so. You can see here, this is age, and this is, I plotted something that has to do with the angular momentum, with the specific angular momentum of the star. The Sun has a specific angular momentum which is given by this vertical line here. So anything that's close to this vertical line, or thereabouts, is moving more or less on a circular orbit. I can see most of these stars, most stars around the Sun, are actually moving like the Sun, more or less circular orbits, which is not surprising. The disk of the galaxy dominates locally. Okay? What's interesting is that this now shows age. You can see there are stars, as old as the universe, which are moving around in circular orbits. Actually, the stars older than the universe, they're moving around in circular orbits. There are stars of 17 giga-years that are moving around in circular orbits, which just clearly shows that there's still some tension between how you measure stars through just isochronous fitting and how you measure the age of the universe, in cosmological terms. And of course, there are error bars which I haven't plotted here, so there is not, a glaring discrepancy here. But the point actually remains. There are old stars in the disk that are moving around on circular orbits. So how is it possible then that I can reconcile this, idea of early merging activity that presumably, if you take this as face value, did not happen in the Milky Way? So that's the kind of things that motivate us to look into, what we can learn from the simulations in more detail. So let's go back to the simulation where you had, remember, this disk of stars, and I changed the colors now. Red now means gas, so you can see a disk of gas, and you saw that this disk of gas actually is also tracked by the young stars, and then there's also a spheroid of older stars. Okay, so that was the final output, if you want, of the movie that I showed you a few minutes ago. So now we can, of course, we have everything in the simulation. We look at everything. We can measure everything we want. So one thing we can measure is, for example, the specific angular momentum of a star or of a particle of gas around the z-axis, where the z-axis is just the rotation axis of the disk. Since the disk is well defined, this has actually no ambiguity. So I'll measure how fast the thing is going around the rotation axis of the disk, and I'll also measure its specific energy. This is for those of you who are old enough to have studied Trampler and Weaver. This is what's called a Lindblad diagram. Okay? And what you see here is that all the stars, are in a very well-defined part of this plane. And the part of this plane is, of course, bounded, at any energy is bounded by 2 points. The circular orbit, co-rotating circular orbit, and the counter-rotating circular orbit. So they have to be between these 2 points. And you see the gas, sort of hugs this line over here, which tells you the gas is going around on circular orbits. Okay. Now, stars, of course, can populate almost all the available space. Now, in order to make more quantitative, progress, we'll define a number, a parameter, which I'll define as the circularity of a star by taking a star, measuring its specific energy, its angular momentum, and dividing by the angular momentum of the circular orbit of that energy. That's a number that will go between 1 and minus 1. 1, you're in a circular orbit. Minus 1, you're in a counter-rotating circular orbit. 0, you have no net sense of rotation around the z-axis. Okay? And I'll just do a histogram of that for all the stars now. The gas is all on circular orbits. And this is what you see. And clearly, the morphology that we saw over here, a disk, and a spheroid, is clearly shown here as well. There's a bunch of stars at around 1. This is the disk. And there's a bunch of stars actually counter-rotating. These are negative values of this parameter. Okay. You can see this kind of Gaussian-looking thing. Think of this as a Gaussian-looking thing plus, a peak at 1. And this is the spheroid plus the disk. So we can actually try and make, some kind of dynamical, decomposition into components of this galaxy based using only its dynamics. Okay. So this is one possible one. It's not a unique one. How do I define a spheroid? Well, I can take, for example, all the stars that are counter-rotating, take this distribution of this parameter, copy it on the other side, and then take stars at random from that distribution. That will give me a bunch of stars with no net sense of rotation, by definition, not rotating around any axis, around the z-axis. And if you do that, you take stars at random now from the simulation, you end up having what you expect, a non-rotating spheroid. Now, if you take stars that are almost in circular orbit, you know, 1 plus or minus a little bit, then you obtain stars on a thin disk, like this one. And there's something in between, which you can call, of course, the things have a sense of rotation. They're rotating in the same direction as the thin disk, but not as fast. Okay? And those things are a thicker structure, which you may call the thick disk. This is interesting because in the galaxy, we seem to have something like this, not in the same proportions, perhaps, in the same masses, etc. This is not really a model of the Milky Way, but we can see how these things were put together and learn from this. The thing is actually instructive or interesting is to look at the age distribution now of these stars. So take all the stars in a thin disk, for example, and you saw all these many mergers that this galaxy had up to about 8 giga-years ago or so. And that's when, you know, the major mergers kind of abated, and this disk that you saw at the end started to form. If you look at the age distribution of the thin disk stars, which are selected only by looking how they were moving around, okay, they're moving around on circular orbits, is this one here by this magenta. Okay, so you see it's flat. This is the age or time, and it's more or less flat out to 8 giga-years ago, which tells you that the disk has been formed at more or less a constant rate since in the past 8 giga-years. But you also see this other little bump of stars here. Stars are old, 12 giga-years or so, much older than the age of the final major merger, but still on circular orbits. So where do these stars come from? Why are there stars on circular orbits that are older than the age than the time of the last major merger? And you can get a clue from that by looking at this other curve, this other magenta curve here. This tells you what fraction of the stars in each of these little bins that I built to plot the histogram were formed more or less close to where you find them today. Okay, they're on circular orbits, so always at the same distance. You can ask, how many of the stars actually formed there? In the simulation, we know everything, so we can actually go and ask that. You can see that this number is about 100% for all the young stars in the disk. So all the young stars in the disk, which are going around on circular orbits, formed more or less at the distance that they are today. These old ones here, this 10 or 15% of stars in the thin disk, that are much older than the age of the major merger, were not formed where you see them today. Actually, all of them were brought in by satellites. All of them, almost, only 5% or so, actually less, were formed where you see them today. They all form in different systems, in different objects altogether. And they were brought in by satellites. How does this happen? It happens because satellites, as these get disrupted, dynamical friction brings them into the center and can actually circularize them before they disrupt them. This is an example. I'm showing you one of the satellites in the simulation that contributes some stars. And what you see here is only the evolution of the stars in the satellite. Okay? Of course, there's the galaxy, the stars, dark matter, there's everything which I've deleted from the little animation. And this is what happens. So the satellite gets in, eventually gets drawn into the disk, it gets circularized, and then eventually gets disrupted. So when it gets disrupted, it contributes orbits, it contributes stars to different kinds of orbits. The colors you see here on the satellite, I'll show you now a face on. This was the age-on view to show you that actually the debris ends up on a disk. The other one will be the same thing, just seen face-on. You'll see how this thing evolves, gets turned into a circular orbit before it gets disrupted. The colors you see here, I'm only showing the stars. And the colors you see here actually show to what component these stars belong to. If you see a star that's red, it will contribute stars to the thin disk. In other words, it will end up on a circular orbit, more or less. If you see a star that is, blue, it will end up in the halo. It will have, a much less degree of centrifugal support. You can see this satellite, this particular satellite, of which are many, so there were hundreds of little mergers like this early on, actually contributes a bunch of stars more or less on a donut. Okay? So stars are going on circular orbits on a particular place, which is the site where the satellite was disrupted. The core of the satellite, which survives until the end, contributes stars more or less in circular orbits. Of course, there are many other stars that contribute that are not in circular orbits, which have different colors now. But this gives you a clue of how you can actually have stars that are older now than the age of the merger and still going around in circular orbits. they were brought in by satellites. Interestingly, you may have heard of mergers contributing stars to the halo streams and the Sagittarius stream, and many in this institute actually have been very active finding and analyzing these streams. What I'm telling you is now the streams actually may also exist in the galactic disk, not only on the galactic spheroid. So, this may sound kind of odd, but it's actually quite interesting. So let's have a look at that. How do you find, how can you find these tidal relics now in the galactic disk rather than on the galactic sphere? And in the galactic sphere, in a way, it's easier. You just go and look. If you see something that looks like a tidal stream, well, it might very well be a tidal stream. And there's, with the publication of the Sloan survey, there have been hundreds of these streams, found in different, in our galaxy and in others. Okay. Well, if you go to the disk, it's harder, okay, because you go to the disk, you take a random sample of stars around the disk, and they're all like the sun. They move like the sun. They have the same metallicity as the sun. They are kind of like, trying to learn about the genetic variety of a population by looking only at your own family. You're not going to learn a lot. So in order to find these, odd events, you may well want to bias your samples and go to things that are not like the typical star in the solar neighborhood. One thing you can do, for example, is look for metal poor stars, for example. Those are not like the sun. Or stars that are not on the disk, above or below the galactic plane by a little bit. Or stars, at large galactocentric distances. If I had, more time, I'd probably go through each of these things in detail. Let me just take the metal poor stars, which I think make an instructive case. Metal poor stars, this is a compilation by Tim Beers and collaborators a few years ago. And what they did is just take a bunch of stars, find them because they're metal poor, and then measure the distances, kinematics, etc. Okay, so you have some estimate of the metallicity. They're all metal poor, so not like the sun. And they have some distances and velocities to actually compute an orbit. From this orbit, you can actually measure, for example, its rotational speed. These actually stars are very close to the sun. So if rotational speed is close to 220, around over here, it will be like the sun. The sun is now marked over here. 220 is marked over here. So stars like the sun will be here. And all I'm doing is a histogram of these metal poor stars. Okay. And the thing that you should take from here is that these stars don't move like the sun. Okay. They are all lagging the sun. Okay. So the whole rotation speeds are less than 220. They're not going as fast. In other words, they're not going on circular orbits. Okay. It's not particularly surprising. That's what you see. Interesting thing is that if you now decompose these things into, the disk, the thin disk, and the halo, you still have these kind of bumps over here. So you see a bump over here, there's a bump over here, bumps over here. So it's like this distribution is not really, homogeneous. We'll get back to that in a second. The other thing that's interesting is that for a subsample of these stars, you can actually go and measure not only some broad estimate of the metallicity by making some calibration. So, for example, one spectral feature, like the calcium triplet, you can actually go and do high-resolution spectroscopy. It's much more expensive in terms of telescope time, but it can be done, and measure other elements, not just some surrogate of iron, for example. When you do that, what you find is that you say, for example, look at the family of elements that are produced in supernova type 2, the alpha elements, and you make a plot of the abundance of this alpha element to iron, how many alpha elements you have per unit of iron. In terms of iron, you end up with this plot like this. And all this is referred to the sun. So the sun is over here at 0, 0. It's logarithmic measures relative to the sun. So 0, 0 is the sun, which is right there. And you see that all to the left of the sun, they have to be chosen to be metal poor, so to the left of the sun, but also above. So they're all, as they say, alpha enhanced. Okay. And the more metal poor you are, the more alpha enhanced you seem to be. Okay. And that's, of course, and if you've been to talks like this one, I'm sure you have, this is the whole idea of, some kind of chemical enrichment process in the stars in the solar neighborhood, where you started with things that were polluted mostly by supernova type 2, which produced lots of alpha and not a lot of iron. You start over here, you start moving to the right, as you become more metal rich, you're alpha enhanced. At some point, supernova type 1a, which produces a lot of iron but not a lot of alpha, started kicking in, and you start moving to the right faster, but also down, because you're not producing a lot of iron and not a lot of alpha. So this kind of, trend is more or less what we expect in a system which is, polluted by these two different kinds of processes. And the place where this kind of bends from more or less flat to more or less steep it tells you when, what metallicity supernova type 1n, what type 1a started kicking in. Okay, so that's the typical idea of this. There are, of course, rivers of ink printed on the papers about this kind of interpretations. Okay? And it's all, all and well. Until you look at things like this, for example. These are now, instead of having thousands of stars, because this is much more expensive, only hundreds of stars, where you can do this, with, and you have good distances and good orbits as well. There are fewer stars who can do this. There are only a couple of hundreds of these stars. You just do the same that I did for the Tim Beers thing. Just take a specific angular momentum or rotational speed. It's the same. All the stars are fairly nearby. And you just plot it. And this is what you see. You see the distribution of angular momenta is definitely not random. You see these peaks here. There's a peak of stars which are actually slightly counter-rotating. There's a peak of stars that have angular momentum about half that of the sun. Half. So, right, it's moving around this. It's very close to the sun, but it's moving around the sun, around the center of the galaxy at half its speed. So it's only passing through its neighborhood. It will actually, it's in a completely different orbit. It's interesting to note that there are a couple of interesting examples of this. You can actually look from the northern hemisphere, just with naked eye, at least one. This is Arcturus, for example. Arcturus is a funny star. It's moving with half the speed of the sun around the disk, around the galactic center. It's, of course, on the disk. It's very close to the sun. It has a very, very small vertical velocity, so actually it's more confined to the disk, but it's on a very different orbit. Okay. Sorry? N is a number. It's a number stars in each pin. It's only about 15. So overall, there are only 200 stars. So the peaks are not big, cannot be very big. The statistic significance of this peak is debatable. Okay, so I'm only going to show you things that are suggestive more than statistically conclusive. But it could be no real, could be, could be not. That's what I'm saying. That's statistically debatable. So let me show you why this might actually be more interesting than just a statistical coincidence. Is by looking, for example, at what happens if you take those stars, only the stars in this peak, and you plot them in this plot again. They're not in a random place. Okay, so the stars which have been, I now have chosen them, these red stars over here, I've chosen them to have the same angular momentum as Arcturus. They're actually not distributed around over here. They're actually much narrower. And you can do all sorts of fancy statistics, which, since you only have 200 points, you'll never be convinced of any of them anyway. But, for lots of statistics, you can actually convince yourself this is not a random sample of the population. You see, the stars seem to know, or at least the suggestion is that the stars seem to know about themselves, not only of their kinematics, but also of their chemical properties. The interesting thing about this is that this other peak over here actually corresponds to your old friend Omega Cen, the most luminous of the globular clusters, also on an odd orbit. It's actually an orbit has an apocenter which is inside the solar circle. It's actually very close to the plane. It doesn't have very high z velocity, but it's going almost in and out of the center of the galaxy. It's on a very odd orbit. And because of that, people think that Omega Cen did not form there. It actually formed as part of the nucleus of a bigger galaxy that has now been disrupted, and this now all we see is the central object, the central part. Another reason why people think that is because Omega Cen is one of the few global clusters where there are several populations of stars with different metallicities, different ages presumably as well. And so it's interesting that these stars, which are now on the solar neighborhood, seem to have at least the same kind of properties as at least angular momentum as Omega Cen. If you do the same trick, you just take the stars in this peak and you look at them where they are on this plot. There are these green ones. They're also not in a random place. They also seem to follow, a single track on this plane, which would correspond, to just a single self-enriching population of, which could have been, for example, a dwarf. But it's interesting that, by doing this, just and identify these two peaks, you can actually put almost, 15% of all the stars into two little streams, okay? And say maybe. And then the bold in you comes in and says, okay, well, why not all of these stars come from different satellites? And they're all actually formed in totally disjoint places, which have nothing to do with each other. Okay? And all these ideas about the self-enriching and this chemical elements being mixed and stuff in the star neighborhood might actually not be correct. So clearly there's a lot of stuff to be done, and there's very few stars here, so it's actually hard to convince yourself that this is true or not true, but I think it's actually still suggestive. So let me leave you with those thoughts and move on to other things, like satellite galaxies and what we can learn from looking at the simulations or looking at the satellites. Okay, so I'm not looking at now things that are being disrupted and destroyed. I look at things that have survived. Okay? So you can see this over here. This is a bunch of simulations now, 4 of them. What is plotted here in blue is stars that are formed in the main galaxy, in the main progenitor that you can track, a long time and remain there. Okay? So these are in blue. In red, you see the stars that formed in different satellites, in different places, but now those satellites have now been disrupted, have been destroyed. You see they form this halo, and this is, of course, the idea and why we think that the halo, stellar halo of the Milky Way was formed from the disruption of, pre-existing objects. And the yellow things are things that, of course, survive today as satellites. They can see as self-bound structures, very clearly and easily identifiable. So concentrate on those now. Let's look at the orbits. The orbits, you may have heard of you may have, imagine what the orbits are like. The universe is expanding. A little satellite that will, at the end form part of the halo of the Milky Way will initially expand away. At some point, because it's bound to the galaxy, will reach its maximum distance, and it will turn around. Okay. In the time that this happens, the main galaxy, the main progenitor of the galaxy, is growing and growing and growing in mass. Things keep falling onto it. It keeps growing and growing in mass. One way of measuring the size of an object, the mass of this galaxy as it grows, is to measure how the virial radius increases with time. Remember, the virial radius is the radius where a circular orbit takes about the age of the universe at that time to complete one orbit. Okay. So it's basically a surrogate of the mass, if you want. So I'm plotting here the virial radius of the progenitor and the orbits of 2 satellites. Okay. One that survives and one that doesn't. So the one that doesn't is this one here, goes to turn around, the maximum distance, and then collapses into the galaxy, does a bunch of things, and then eventually disappears. Okay. Another one is this one. Okay, actually survives. This survives to the end as a self-bound object, and it goes around a couple of times. Interesting things you can see here is that the turnaround, the first orbit, first time it went off and it came back, is the maximum distance it ever achieves. Okay. Because dynamical friction only, basically robs you of energy. It wants to make you, more and more bound to the center, to the main galaxy, and not less and less bound. So in other words, the apocenter is always decreasing with time. The maximum distance decreases with time. Of course, because it's very fast in this case, the satellite merges, less fast than this one. The main difference here is mass. Satellites are very massive. Dynamical friction brings them in very quickly. Things that are less massive takes a long, long time. Okay, and that's why the ones that survive tend to be a biased part of the population that ever fell in. Okay, so this actually has interesting consequences. Look at this, for example. This is the mass. This is a distribution of masses of things that have survived and things have disappeared. Things have merged to form, the stellar halo, or even parts of the disk, as I just described before. And in green here, which you can barely see, is the ones that have disappeared, have merged. And what you're plotting here is the ratio of the satellite mass to the host mass. So you see if this number is big, this would be 1, this would be, about a half. Now it's big, you all disappear. That means that all the ones that are very massive, they take only a few orbits to be merged into the main object. The ones that are low mass, these red things over here, this is 1/100th of the mass of the host, can survive for a long time. So in other words, if you look now at the halo stars and compare them with satellite stars, you'll find 2 different populations. They'll be actually different. And this has, of course, been known for quite a while. This plot I stole from my colleague, Kim Ben. And it shows this alpha over iron plot I showed you before. This is for stars in the galactic halo, or actually in the vicinity, but have kinematics which are consistent with not being in the disk. And these are stars in dwarf spheroidals, in satellites. And people notice that they're not the same, they're different. Okay? And the argument here is that this might be the cause of the difference. The ones that survive in satellites today are a very biased sample of whatever fell in during the history of the accretion of the Milky Way. So, okay, that's not perhaps too huge a surprise. Let me show you a couple of things that may be less obvious. Let's talk about the local group satellites, although it's been kind of a revolution in the past few years about this. This is the view of the local groups as of about 9 years ago or so. And a couple of things you want to note here. First is that these are colored. This is the Milky Way. This is M31. And these are colored by their kind of satellites that you see. For example, these orange ones are the dwarf spheroidals. Those tend to be clustered very close to the main two spirals of the local group. People have talked about the presence of geometrical anisotropies, like satellites all being in planes or not. So we can talk about this a long time. I just want to talk to you a couple of things. One is that if you look at this, actually these dwarf spheroidals seem to live near the sides of the main spirals. But there are also some which are oddly, very far away. Tucana and Cetus are two examples. Actually, experts here have looked at, lots of internal properties of this. It's odd. These things are in the middle of nowhere, right? They're really far away, megaparsecs away from the center of the galaxy. What are they doing there? Why is it that there seems to be this dichotomy? Most of them are here, but a couple are floating about. So, because of those kinds of things, now we started looking at the distribution of our own satellites in the simulations. We go to the simulation and say, well, I'll look at all the satellites that were part of the main object. At some point, they fell into the main object, and I'll just put a little box around them. Of course, they'll survive today. Now, this is a redshift 0. The virial radius, and this radius where things, defines the region where things are more or less virialized, is encompassed by this box. And everything that has a little box around it is a satellite has been at some point inside the virial radius. As you saw before, it's unlikely that something has been inside the virial radius will ever get out from those orbits that I showed you at the beginning. But there are several actually outside. 1, 2, 3, 4. How did this happen? Why did the satellites that were inside the main body of the progenitor at some point came out? What is it that led them there? This is one clue. Okay, you can track the orbits, of course, of this satellite and see what happened. The orbits are for two of them. This dash one, look at this dash one, that came in, went to the pericenter, and then was ejected out. There's another one here. When it turned around, came in, was ejected out. I see there is another one that actually tracks almost the same during its accretion. These satellites are coming in groups. They're coming in pairs or more. And you can actually track them here in this little animation, this little movie, where actually it's the same simulation. I can do many things with just one simulation, it turns out. And where I've put little boxes around each of these little satellites, and all I'm showing you is the stars. This gas and all the rest. You've seen the movie before. So just look at these two stars. They're formed together, they're orbiting around each other, and when they approach the center of the main galaxy, because of the phases of the orbits, one of them is able to grab orbital energy and to be ejected out of the system. You see how it goes much further than it ever was before. In other words, the disruption of the bound group of satellites will lead some of them to acquire orbital energy and be ejected out of the system. And this is not something that happens. This is another example, the other little pair that I showed you before. Again, it's the same simulation, just different perspective. These are the two satellites, are born bound to each other, that actually orbit a couple of things around, a couple of times around themselves on the center of mass. And look at how, when they approach, one of them, the one that's farther out, will actually start approaching the apocenter of the whole group's orbit at the same time it approaches the apocenter of its own orbit around the group. It's because of that phase coincidence during the orbital that this one gets ejected out, and the other one, of course, remains bound. This thing actually happens, fairly often. It actually happens all the time. It's because of this hierarchical clustering idea. The satellites are not coming one by one. They all come in groups. When you throw a group of things that are bound into something that's it's more massive, the tidal disruption always leads to the formation of tidal tails. These tidal tails are the parts of the system that have gained energy, at least the outgoing tidal tail. This tidal tail, if you throw a bound group of satellites, some of them will gain orbital energy, some of them will lose. The ones who gain turn out to be most of the low massive ones, and those are the ones that get preferentially ejected. Okay? So one can now make I can see this over here. This is a single group of satellites. Actually, there are 1, 2, 3, 4, 5 satellites. I can see how they all orbit. This is distance versus time. They all orbit around each other. They approach the epicenter of the main object, and the group gets disrupted. And each of them goes into a different orbit. Some of them get ejected, some of them get more bound. And you can see over here, this is at the final time. This is radial velocity versus distance. You can see how the main group was disrupted. This is a tidal tail. You see how many of the satellites actually belong to the tidal tail. And some of them are actually ejected. So if you want, because the galaxy, or the satellite system, in this case the galaxy, was put together hierarchically, you expect these events all the time. Some of these things must have come in groups that were disrupted and were ejected, and some of them were ejected out of the system. So it makes it a very tempting case to try and ascribe some of the kinematical oddities in the local group to this kind of process. For example, there is a case of Leo 1. Leo 1 is a satellite that is a couple hundred kiloparsecs, but it's moving out, moving away from the galaxy at more or less 200 and something kilometers per second. That's actually very odd, the state of affairs. It's almost at the escape velocity of the system. How did that happen? How did the satellite acquire suddenly the escape velocity? This gives you, an idea. Now, to finish here, talk a little bit about this. Let me tell you about some heretic idea which I've been working on the past couple of months, which is an origin for hypervelocity stars. Hypervelocity stars are like Leo 1, stars that are in the halo of the Milky Way, but which have a velocity which is completely odd. This was discovered by a group at Harvard, Warren Brown, Margaret Geller, and collaborators. What they did was go through Sloan, take the Sloan footprint, take all the point sources, cut in color by the point sources so that they actually correspond to B stars being basically bright, and go for those colors and look at the faint ones in apparent magnitude, and look in regions that are away from the galactic disk, which is easy because Sloan is all away from the galactic disk. And then you just go and measure velocities for all the stars. Those are basically B stars. If they're main sequence stars and they're faint, because you're choosing to be faint, they have to be far away, they're in the halo. They're far from the center of the galaxy. And what you do is you measure velocity for hundreds of these stars, and this is what you see. This is a histogram of their velocities. As you expect, these stars in the halo, they have more or less, this is a radial velocity, of course, the only one you can measure, refer to the galactic rest frame. And they're, kind of a Gaussian-looking thing. You expect around 0. Some are coming in, some are going out. But there's a tail of stars that go all the way to about 700 kilometers per second. And when these were found, the association was made. How do you put a star that is at, 100 kiloparsecs from the center with 800 kilometers per second or 700 kilometers per second? The association was made that these were actually ejected from the galactic center. Okay? So basically a binary gets formed, gets close to the galactic center, and the supermassive black hole of the galactic center disrupts the binary, and one of them gets ejected out. Okay? A very persuasive idea. The problem, or not problem, but there's some oddities in this idea. This is actually what it looks like. This is galactic coordinates. This is the footprint of Sloan, of course. These are all in dots. You see all the stars with measure velocities selected by this process I just said. And these are the ones that actually have, the ones in color are the high velocity stars. All the stars with velocities basically larger than, 300 kilometers per second or so. You plot them in the sky, and what you see is that they're not actually isotropic. They're not a random sample. And again, you can do all sorts of statistics here. The numbers are small, so you'll never convince the true skeptic. True skeptics, die without convincing themselves of anything. But you'll see that there are actually some of them, actually almost half of them, clustered in one constellation of Leo. It's another oddity as well, which is now we have distances and we have velocities. We can divide one over the other. I'll give you a time. That's the time it takes for a star to go more or less from the center to that location. I'll do a histogram of that time. And this is a histogram you see over here. They're actually all peaked in one point. It's like they all have the same travel time. It's like all the ejected more or less at the same time from the center, all in the same direction. That's odd. You put the two things together, it gives you this fuzzy feeling in your stomach saying maybe there's something else going on here that is not just this supermassive black hole spitting things out like prune pits. And the obvious thing is this one, a tidal tail. A tidal tail you get a satellite, you throw into the center, it gets ejected, or a bunch of stars get ejected, they all get ejected at the same time, at the time of passage for the pericenter, and they all get ejected in one direction, the direction of the tidal tail. Okay? And you can ask, how fast can stars go in these tidal tails? But typically the fastest stars, and this is an example just from the simulation, this radial velocity, these curves over here are the escape velocity. These funny things you see are actually bound satellites. The fastest stars you can get in this tidal tail here go out to about the escape velocity. The escape velocity of the Milky Way, if you believe this kind of cold dark matter halos, which I should have pointed out here, escape velocity of the Milky Way is about, 500, 600 kilometers per second, even at 100 kiloparsecs. So these stars, of all these stars, if this is true, of all these stars, the only one is unbound is this one. If you go to this plot over here, you see there are even some stars in these tails which are unbound. And they all have a very particular print on the sky. Because they all go in the same direction, it's a tail, after all it's a stream if you want, they all appear in the same direction of the sky. This is what this particular thing scaled to something like the Milky Way would look like. Would look like, almost spanning a whole constellation if they were at about 100 kiloparsecs. So, we put this thing together when we wrote an update letters, and interestingly enough, and I was talking to Warren Brown about this in Santa Barbara a couple months ago, and they had just submitted a letter as well, arguing, making the point that there is something very odd going on with these high-velocity stars because they are actually concentrated mostly on one particular part of the sky. And this is something that does not sit very comfortably with at least the most naive models of ejection from the galactic center. So let me wrap it up here, just to leave you with the idea that there's a lot to be learned just by trying to piece together, how the galaxy was put together, and the idea that there are many events of accretion that may have led to even maybe have brought a star like Arcturus all the way into our solar neighborhood. It's actually, I think, quite appealing. So I hope you take this as not particular demonstration that these things are actually completely true, but as inspiration that these things may have happened, and that with enough work we should be able to puzzle out how the galaxy was put together. So thank you.
Okay, so there's time for questions.
I have a couple of questions. So the first one related to these hypervelocity stars. We can make the argument reverse and use these weird stars to try to make a better measurement of the halo potential, for example? So we can put any constraint on the halo potential using these stars?
One could, and people have written papers on this, trying to look at, for example, if you assume they come really exactly from the center, and you can measure proper motion, then you can measure a three-dimensional motion of the star. If the potential was exactly spherical, and it comes exactly from the center, then it can only move in a radial orbit. If the potential is not spherical, it has to move in something that's different from a radial orbit. Okay, so this argument is very crude, but that's more or less the way it works. So if you see the star moving, on an orbit that is not radial, then you can put some constraints on the shape of the potential, for example. So that has been done. People have also tried to use this as, estimates of the mass of the halo. For example, Brown et al., when they discovered all these things, they argued that most of the stars were actually unbound. Oops, I'm not sure exactly where I am here. Let me go back to my... They made the point that most of the stars are actually unbound because we're using a mass for the halo, which is actually quite low. So if you use a mass for the halo, which is 5 times 10 to the 11, I'm going here into more detail than you may want. This is the escape velocity for 4 times 10 to the 11. Okay? So all these are unbound. But if the mass for the halo is, a couple times 10 to the 12, which is, sits better with one thing from cosmology, although it's not proved, this is the escape velocity. So none of the stars is unbound. They're all in the potential, moving with things like, are consistent with canonical processes. So, if you believe my argument, this is a tidal tail, you can already tell that the mass of the halo has to be quite large. because you're not going to find, thousands, hundreds of stars moving way beyond the escape velocity through, the destruction of a dwarf. Maybe you can find a couple, but not very many. So, I mean, with these indirect ways, you can actually make some progress.
My second question is related to the previous point about the systems that are leaving the Milky Way or the local group, no? These satellites,
right.
The unbound satellites. So the mechanism that you have explained could be, in principle, also sought to be working on larger bound groups, like, for example, galaxy groups or galaxy clusters. So would you expect also to find, for example, in a galaxy cluster, galaxies that are leaving the cluster for the same reason?
Yes, I mean, this is a completely general prediction from hierarchical, scenario. You form things by putting things together. These things you put together, if they have subcomponents, some of the subcomponents will be ejected, some of them will be retained. In a galaxy cluster, I mean, it's something that actually a paper we wrote with Mike Balog, actually many years ago, is in the galaxy cluster what we can do is, take the galaxy cluster, look at the virial radius, and say, oh, this is my virialized region, and outside I should have just the field. Things are just coming in for the first time. That's your naive thinking. So in other words, you can take, the sample galaxy in the cluster, and then take the sample at maybe twice the radius, twice the virial radius, and say this should be the field. When you do that, you find that many galaxies that are not like the field, even twice as far as the virial radius of the cluster. You need to go way farther from the cluster in order to find something that looks like the average galaxy population. So in other words, the cluster is polluting its environment with galaxies that know that the cluster is there. And this is, one possibility, that the cluster was put together through groups. Some of the galaxies were already processed in groups, were thrown out, and those are making the environment, the near environment of the cluster, much more like the cluster than the field.
Yeah. So then my exact question is, can you provide a number, a percentage of contamination of these galaxies that are going away or so that we can go to observations and check it out, for example?
Yes, the numbers depend a lot on mass. The things that get ejected, preferentially, the things that are low mass, because are the ones that have, the largest oscillation of motion around the system. Think of the simplest case, a binary that is coming in, a binary satellite. One very massive and then not massive. The center of mass is at the center of the most massive one. The only one that moves is the low mass one. So the only one that can get ejected is the low mass one. So the prediction depends a lot on mass. But we have in a paper written by my students, Aaron Ludlow, you're welcome to look at. We have the numbers, from 1 to twice the virial radius, how many of what masses you expect to have been ejected or not. So the numbers are there. If you need something more detailed, we can always compute it. So.
Yes. Sorry. It's a bit general question. Despite the, in principle, unlimited growth of a galaxy through satellite accretion or other galaxy accretion, we see a limit on the size of the galaxy and the mass. So trying to understand why a galaxy doesn't grow forever, have you ever observed an instance of a galaxy disrupting into pieces or breaking into pieces in any simulation or in both in nature or simulations? Have you ever observed that?
No. I mean, we think we have a good idea why there is a maximum mass in galaxies, and it has to do with the fact that the size of the universe is finite, and now we seem to be dominated by some dark energy component, which limits the biggest collapse of the biggest object. And within the biggest object, we also have ideas as to why there is a characteristic mass as to what's the most massive galaxy. But I mean, it will take me probably way too long to go into all the details. But I think we do have a good ideas of why that is the case. Going to your second question, aside from the fact that, when you throw things together, some parts go out and some parts go in. Most of the galaxies you form through mergers are basically, accretion events. Parts of it, it's true, get ejected out, and I'm making a big deal out of the exception of the things, but most of the mass really does remain bound. So you shouldn't get, this biased impression, perhaps, that everything is, flying out into the. These are really, it's a process that it's very effective at the very low mass end of the spectrum, but it does not really alter the main thrust of of gravitational stability, which is really to build bigger things by putting things together.
In your simulations, in the first ones, you use stars, dark matter, and gas, right? In all the simulations you have shown.
Mm-hmm.
And at a given moment, you change the gas into stars. And I would like to know which is the nominal value of the efficiency that in this sort of model used to be used. Which percentage, which fraction of the gas is changed into stars? And also, how does it vary if it varies with time?
What we do is very simple things, really. When the gas collapses to form dense objects like these disks, because we're not resolving any regions of a star formation or anything, I mean, our nominal numerical resolution is, kiloparsecs, so we're not resolving any of these things. We adopt very simple empirical laws, which is we basically take the density of gas, we take its, crossing time, and use those two numbers to derive a rate of star formation, which then we try to match to be consistent with the empirical laws of, for example, Schmidt-Kennicutt. So that's the kind of normalizations that we use. So in other words, everything is normalized so that if you had an isolated disk galaxy that looks like, M81 or something, it would have, a star formation history which would be comparable to, or star formation, instantaneous star formation rate, which would be comparable to the Schmidt law. Those are which all these things are normalized.
I mean, people working in the nearby universe, we know and we try to see which is the real law for star formation in high dense things. For example, we do know that the Smith law is very useful and it's traceable in the disk of spiral galaxies and these sort of things. That is where it has been established. And we know that if we go to starburst regions and dense regions, we don't know if it is working still. So my question is, although, I mean, we all have these caveats, but do you run other possible scenarios playing with this quantity also? What will be the impact in the result of the simulation if you don't use the Smith law and you play with a different laws for star formation that can be more extreme as the one that seems to happen in resolved objects in the nearby universe?
I mean, we have played, a lot with these things. Several trends emerge. The most extreme ones, for example. Imagine that as soon as the gas gets dense, we turn it to star right away, and we make, the feedback, as we call it, the output of energy that the evolving stars have, very small. What would happen then is that most of the baryons in the universe would get locked into stars at very early times, because basically a lot of the mass of the universe is in collapsed objects early on. And so, quickly our 20% of baryons or 17% of baryons get all into stars, which is in violent disagreement with the observations. We know that cannot be right. So the efficiency at which, the amount of gas that can cool goes into stars has to be quite low. So by doing that and by trying to match the empirical laws, one gets a feel as to how things have to change in order to be able to for example, this galaxy, although it looks kind of, it actually looks quite nice. Actually, it has almost 70% of the stars in this spheroid. And that's because the way in which we chose these parameters favors the formation of stars early on. If we had done something different, doing tricks, putting more energy in feedback, etc., and it gets very technical here, but we can actually revert this. For example, if you only allow stars to form very late, the prominence of the disk will increase relative to the spheroid. So there are many things one can play with, and it's very easy to get, lost in what is actually robust about the models. That's why I really haven't told you that I matched anything in particular. I haven't told you this is the model of the Milky Way. I think the simulation at this point, because they have so many free knobs and parameters, are best used as a source of inspiration. What kind of things can happen, and what is the relative importance of different mechanisms, rather than as predictors of say, oh, if I have a halo that has this mass, it has to form the Milky Way or M31. I mean, I think we're way beyond that stage now.
The only way to get something like this is to play with an efficiency of a star formation or a feedback process that's similar to the one predicted by, for instance, the Schmidt law. And if you play with a different number, you don't get to that.
You can get things that are very different, I guess. Yeah. But it turns out that it's not the rate at which you form stars out of dense gas that is most important. At least from the simulation point of view, what is most important is what you do with the energy you think is coming out of an evolving population of stars, rather than, at what rate they turn into stars.
How do you decide whether a particle is part of the thick disk or the thin disk?
At random, from what I showed you here. You have these distributions and you choose particles at random. It does not seem to, since these are fairly distinct, except, maybe this overlap over here, it doesn't make a big difference, at least for this case. I mean, there are cases where, you don't have such a nicely narrow peak here and things get a bit more, a bit more controversial. But as I said, I'm not using this to motivate, this is the thick disk of the galaxy. I'm just saying, how was this, we see a thick disk here, how was it put together? And the interesting thing about here, which I maybe didn't express, is that actually the whole thick disk, the whole old thick disk, is made of debris, of satellites, which is very different from, the typical, party line as to how the thick disk was formed, which is, having a thin disk and bombard it a little bit and gets a bit thicker. There's totally difference, right? All the stars were brought in by satellites. Whether this is true or not, I don't know. But this is the kind of thing you may want to keep in mind while you analyze your data in order to have, less of a prejudiced, interpretation.
Yeah, a couple of questions. The first one related to the figure you were just showing on the thin disk. Is that thin disk all formed from gas in situ, or how much of it? Is there a fraction of this thin disk that came in as stars?
Yes, this is this 15%.
Oh, yeah, okay. You mentioned
15% came in as stars, old stars and satellites, and the rest was basically formed in situ. So about, in this case, which is one case that is, might not even be comparable to the Milky Way, it's 15 to 85. But,
yeah. My main question was, you didn't mention anything on the problem of the size of the disks. How do you see the progress on the question of the compactness of the disks? Common simulations.
That would be another talk, Mark, which you heard me give in Texas a couple of weeks ago. So. It's interesting. What Mark is referring to is the fact that if you take, do the most naive thing in the simulations, which is what I did at the beginning, which is just take the gas, let it cool, and collapse to the center and form these little disks. What I didn't mention is that those disks tend to be much smaller than a typical galactic disk. And the reason is that because you form this thing through mergers, during a merger of two gaseous clumps at the center of two objects, most of the angular momentum is lost. It's transferred to the halo, and the thing that ends up forming is a disk, because you have some angular momentum, but it's so small that the disks are very small. So this puts constraints as to when and how you allow the gas to cool, which I guess goes back to your question. And what seems to be coming out of the newer simulations is that what you need to do is have very effective outflows of mass. In other words, you form these dense things early on. They form stars maybe very efficiently, but those are able to input some energy into their gaseous components and blow them all out. And what is left at the end is really a biased view, a biased part of what came in. The disks that you see today are actually made out of the late infalling material, not the early collapsing material. If you do that, you can get much better agreement. There are a couple of papers, actually even today, I think, or yesterday, AstroPH, showing actually nice movies and simulations for these things. But clearly, you need the contribution, this feedback energy from the baryons to regulate this process in a way that is, I think, we know which way we should go. Whether that's the right way, and it's less clear to me. Right?
Well, just a comment that contradicts what you say, that 90% of all stars in the disk are the result of satellite accretion. When we go to AGV stars, to the Magellanic Cloud, we see always very low metallicity. And we go to AGV stars in our galaxy, we saw much higher metallicity. So I really don't understand how this can be explained with this.
Are you talking about the old stars in the disk? Are you talking about the stars in the halo? What are you referring to?
Well, on the most of AGVs on the galaxy are on the disk.
So you're saying that the old stars in the disk of the galaxy do not look like the old stars in the imaginary clouds. Is that what you're saying?
Absolutely.
Okay. That's fine. The imaginary cloud does not look like the Milky Way, so I'm not really sure how I should make the strict, correlation.
Well, my cloud is a satellite.
True, but a satellite that survived, so the satellite probably is coming in for the first time from very far away. So the connection between the two is not clear to me. But in other words, the progenitors that form the old stars that you see today in the solar neighborhood may have been different than the progenitors that form what is today the imaginary cloud. Right? So I understand your point, and I think it's a good one, but it does not contradict what I said. Right? I mean, but you have to say that progenitors are different.
Yeah, but I mean, for me, satellites should have also low metallicity.
Oh, and the old stars are typically are metal poor too. So you're saying the metal poor in a slightly different way, which I think it's an interesting point, but I don't think it contradicts what I said. In other words, the old stars in the imaginary clouds and the old stars in the Milky Way may have come from different kinds of progenitors. I mean, if that's true, then we have to conclude that. But that's not impossible. In other words, the Milky Way probably was very different early on than the progenitors of the imaginary clouds. So it's not impossible to believe that that's the case.
You always form stars in your simulation or another term, which is the role of dry mergers in forming galaxies?
Dry mergers. Okay, well, if you had lots of dry mergers, basically, for those of you not in the know, a dry merger is something where all you merge are things that are stars and dark matter, and there's no gas. If there's stars and dark matter, no gas. A sequence of dry mergers will lead you to the formation of more and more prominent spheroids. This could eventually get destroyed. Clearly, through that process, it's unlikely to form something like the Milky Way. I mean, this is, after all, what the Milky Way looks like, right? The Milky Way is really this galaxy. And even this bulge, people think that, it's part of the disk somehow. And even if it's not a big deal anyway. So, but really, most of the stars are on the disk. So you're not going to form the Milky Way through a sequence of dry mergers. So at least for the Milky Way, the dry mergers are probably relevant. For other galaxies, though, it may have been very important. And, central galaxies in clusters and groups, etc. So that's a different environment altogether, a different kind of galaxy altogether. So remember, the topic here was the formation of the Milky Way, not of everything. But clearly it's an important issue on other respects.
Questions? Discussion? I have a small question. It's related to the hypervelocity stars, the B-type stars from the Sloan catalog. Do you have an estimation or a measurement of the metallicity and age of these stars? Do they share the same metallicity and age?
The short answer is no one knows. These are faint stars, and you choose them to be faint because you want them to be far away. Right? So these are B stars are typically intrinsically bright. If they really are main sequence stars. Now there may hit the whole talk under the carpet here. These are things that have colors of B stars. The only couple that are really confirmed to be more or less main sequence stars. There may be many blue horizontal branch stars here, hiding about. In which case, the distances estimates are actually completely off. So, and because they're faint, there's really not good metallicity for a lot of them. But it's one of the ways in which you can test whether these things, for example, are really dwarf, the remains of a dwarf or not. If you find that this star over here is as metal rich as a star near the center of the bulge, clearly this has not formed from a small galaxy that was disrupted. So that's one of we say that in the paper. That's one of the ways you can actually tell. There are many ways you can tell whether this scenario is correct. And if after a few beers, I'll tell you that I don't think it's correct. But the referee has said this is true, and it cannot be disproved. But that's one of the ways you can do it. Of course, if this is true, also not only B stars should be ejected. I mean, B stars are there are lots of them near the bulge, and that's why people look for them. But if this is true, you should go and look in the same direction of the sky and find hypervelocity stars which are not B stars, any star. So there are many ways in which you can actually disprove this idea, which I think, at least from the point of view they can actually disprove it, it makes it interesting. But no, the short answer is no one knows yet. But no, it's not impossible. It's just you need to devote a fair amount of time for this.
Okay, thank you. More questions? Discussion? Okay, let me remind you that Professor Navarro will be here at the IC. His office is in the first corridor, just at the end. This is Ramon's office. And also let me remind you that at 12 there is a coffee break upstairs, and you are all invited to attend. So thank you very much. Thank you.